start this, recording. So go ahead.
Okay, so just a few words, don't take much time. Hello, everybody. I'm Katia Gonzani. Just few words to announce that with this talk today, we enter in a new phase of this Zoom broadcasting of the non-commutative geometry seminar. And we have named it the Global Non-Commutative Geometry Seminar. So this Global Non-Commutative Geometry Seminar is a joint effort of few people from three groups or nodes, the Americas, Europe, and Asia Pacific. This group will coordinate the future talks of this seminar, and today is the first one. We expect that early 2021, probably around the middle of January, we shall be ready to run this seminar weekly at least. The Global NCG Seminar will be broadcast in turn from locations based in each one of the three main geographic areas I mentioned before. So that means in turn from locations in the Americas, Europe, and Australia, China, Japan. Each group will present a speaker. The main goal is to keep in touch and at the same time be aware of new research in non-commutative geometry in these difficult times when traveling is hard and risky. The Global NCG Seminar has also a forthcoming dedicated web page where talks are announced and supported with relevant material such as abstracts, perhaps slides, references, comments, suggestions, etc. This web page will also contain links to YouTube videos. By the way, the last email announcing today's talk made a notice already of this new YouTube channel already running, dedicated to collect videos of talks in non-commutative geometry. The organizer of the Americas node, the group presenting today's speaker, are Guillermo Cortinas, Nigel Hickson, Masoud Kalkali, Jean Tang, Wan Liu, and myself. I finished. So now it's my pleasure to introduce Henri Moscovici, speaking about differentiable characters and Hopf Cyclic Cohomology. Thank you.
Thank you. Thank you, Katia. So according to the global local principle, we pass now to the local talk. So, I have to do something with the preview now. Okay. All right, so what I am going to do today is a sort of retrospective of a topic which started about 20-some years ago. And it developed in some direction, but it stopped developing in some other direction. So the real purpose of my talk is to start to resuscitate research in a certain direction. Because otherwise, practically everything I'll talk about is based on known stuff, and which is discussed in many papers, and I will indicate some of them. So what is the idea for this retrospective look is to make the analogy with the classical developments in the theory of foliations, characteristic classes of foliations, not really the geometry of foliations, to make it more transparent, because I think it can help progress in our non-commutative direction too. So as I wrote here in the classical theory of foliations, the geometric classes are constructed really in what's called the differentiable cohomology of the classifying space for the Heffliger groupoid of diffeomorphisms of a manifold or Rn, which is computed by algebraic means either in terms of Gelfand-Fuchs cohomology of the Lie algebra of formal vector fields, or in terms of the Weil algebras associated to the general linear group. Okay, so a similar pattern is happening in the non-commutative approach. And as we know by now, I mean, people working or interested in this subject, the replacement of Lie algebra cohomology is Hopf algebra cohomology, which appeared in connection with the index formula, local index formula for the hypoelliptic signature, but I'm bypassing because that's a topic which is rich in sort of notions and explanations. So I am skipping all of that, and I'll try to justify the appearance, the sort of naturality of the appearance of this Hopf cyclic cohomology, starting from the point of view of relating it to the differentiable cohomology, just like in the classical case. So this is the idea. And I think it has some little benefits, which I hope to discuss at the end of the talk. So, as I said here, the basic constructs and notions and constructs I'll talk about are not new, but I just want to sort of present it from a slightly different point of view, with the hope that it can lead to some progress. All right, so the paper which really started everything in this business is Alain's transverse fundamental class. I don't know if you can see. Let me see. I cannot see. Okay. Cyclic cohomology in the transverse fundamental class in 1983. Well, it's not just the transverse fundamental class. This is a paper which brought in Gelfand-Fuchs classes and all most of the beginning of the technology, and in fact, not just the beginning, but it developed a lot of stuff which put the right apparatus and notions in light to develop the theory of characteristic classes for leaf spaces of foliations. Now, I'm listing here the papers which are pertinent for my talk, but not all the papers which are related to the subject, because there is not enough room to do that. But anyway, just to say a few words about each of these papers. So Alain's paper is really the seminal one. And then the Hopf algebra, which I'm going to recall today, and the Hopf cyclic cohomology for that algebra was introduced in connection in the second paper of Alain and myself in connection with the local index formula for the hypoelliptic signature operator. And the stuff which I will discuss today also will use, I mean, as one of the main references, Sasha Gorokhovsky's paper on secondary classes and cyclic cohomology of Hopf algebras. And in fact, what I want to show is that his construction gives a counterpart of the Weil algebra technology in this game, analogous to what Alain and myself did with the absorption of the Gelfand-Fuchs Lie algebra cohomology in Hopf algebra. And there are two other papers which play a role in what I'm going to discuss today, 5 and 6. And so let's get to the basic notions first. So the notation and the basic notions are the Lie algebra I was referring to of formal vector fields is the one which is well known. So these are vector fields on Rn coefficients series. And it's a Lie algebra under a natural bracket. And besides this Lie algebra, we will also use, need to know about these Weil algebras only for the GLN. And its truncated versions. So the Weil algebra and the Lie algebra have also relative versions. Cohomology, I'm talking about their cohomologies. They have relative versions, and for that we will need the relative Weil algebra relative to the orthogonal group. In fact, I'm saying orthogonal group, but frankly, everything will be about the SON, special orthogonal group, because I'll work with orientation preserving diffeomorphism, in fact, without saying it. Okay, so another little thing about, to recall about these algebras is that the Weil algebra sits naturally inside the complex of the Lie algebra cohomology for formal vector fields, because there are universal curvature forms, theta ij's, which are just dfi over dxj here, the coefficients. And out of them, so this gives a connection in the sense of Henri Cartan for this algebra, Lie algebra, and the universal curvature forms Rij together with these connection forms, they generate inside the complex of cohomology, which is the exterior algebra, if you want, of the Lie algebra AN. They generate a subalgebra which is isomorphic with the Weil truncated by algebra, the last one here. So the subscript C under this complex refers to the fact that it's continuous with respect to the natural iadic topology for the series coefficients. So it's using this topology, which is crucial because otherwise it would not give the right finite dimensional cohomology. Now, as I said already, having this universal connection in the Lie algebra gives an identification of the truncated Weil algebra, truncated in dimension n, to what the universal curvature and connection and curvature generates inside the complex, and also passing to the relative version, you get a copy of the Weil algebra. And this is how Gelfand-Fuchs computed the cohomology, in fact, of the Lie algebra. Oh, I repeated it. No, I put an extra ON here. So the cohomology of the truncated Weil algebra is isomorphic to the cohomology of the Lie algebra AN. There is no relative here. And if you take the relative case, then it's the same result. This is the Gelfand-Fuchs result. And this isomorphism allows one to compute these cohomologies because it's easier to work with the Weil algebra, which is a sort of smaller object. All right, so I'm recalling this fact. Another fact which I have to recall is that all these are related to invariant forms on the jet bundle. So if you take any manifold M and you take the group of diffeomorphisms, let's call it this script G, and if you form the higher frame bundles, which are forms from jets at 0 of local diffeomorphisms from Rn to M around 0. So you get this sequence of fibrations, and the sequence defines the formal frame bundle F infinity of M, and the quotient by the orthogonal group, the general linear group embeds in all of them. So the quotient by the orthogonal group gives what's called the matrix bundle or the formal matrix bundle. I mean, P1 of M is the metric bundle, and P2, P3 are its higher versions. So the group G acts on these jets, and one can identify in a natural way the complex of cohomology for the formal vector fields with invariant forms on the full frame bundle, formal frame bundle, invariant under the diffeomorphism, and the same in the relative case. All right. So another technical tool which we'll need is to work in the simplicial context. So if G again is the group of diffeomorphisms, or any group of diffeomorphisms acting on M, there is a simplicial manifold associated to it. And I'm recalling here, in fact, the simplicial structure. Out of it, one can construct two kinds of realizations of this topological realizations of this simplicial space. One of them is called the thick or fat realization. And this is the second one. This one, which gives what we call the Bott complex. I don't know if the topologist calls that. It's associated to another realization, the thin realization. But anyway, the version which is relevant for this discussion is the one which will be called the differentiable version. So on the next slide. But before passing to that, let me also point out that there are two de Rham complexes associated to this. To the thick realization, for the thick realization, you have DuPont's complex, de Rham complex of what's called compatible forms, and the compatibility condition is written here. And the Bott complex is a de Rham complex associated to the other realization. So we'll need both, in fact. The differentiable version refers to differentiability in the sense of continuity with respect to the jet topology. It is the same kind of continuity which is built in the Gelfand-Fuchs Lie algebra cohomology, where the coefficients of the series are formal series. So the same, as I mentioned already, since the Lie algebra cohomology is identified with something on the jet space, in the invariant forms on the jet space, is normal to carry everything in terms of the jet bundle. And then the differentiable cochains will be those which are continuous with respect to the similar kind of cohomology. In other words, the coefficients in local expansion of those forms depend on finite order jets. And it's the same for the DuPont complex, the same kind of condition. And then just copying the proofs of the classical isomorphism between the cohomology of the DuPont complex, Durham complex, and of the Bott complex, they work out for this subcomplex of differentiable forms. Differentiable in the sense which I already said, it's a continuity condition with respect to another compatible topology. Well, since everything is done in terms of algebraic homotopies and stuff like that, they immediately transfer to the complex of differentiable cohomology. So this D here refers to the differentiable cohomology, which is the cohomology of the differentiable Durham complex. Now, the word differentiable is used here in the sense which I said, because otherwise everything is differentiable from the beginning. All right. So now, if we fix a torsion-free connection, then you get a cross-section to the projection from the frame bundle to the first, from the formal full frame bundle to the first frame bundle. Then this cross-section is defined by taking the exponential map with respect to it at every point x. And then if you take a frame U, which is an isomorphism of Rn to the tangent space at x, so you can compose it with the exponential map at x, you take the jet, and this is how you get a cross-section to the projection. And then you can define for every simplex, T refers to T0, T1, Tp, a simplex, a P simplex, you can define a map from simplices times the frame bundle. And with it, you get a map from the simplicial realization of the frame bundle, and then you can pass to the matrix bundle. And then you can define a chain map. I said that, okay, you can define a chain map from the Lie algebra cohomology complex. I will work with a relative version all the time because this is one which is relevant for foliations, not just for framed foliations. So you get this map and sort of mimicking in a way a classical proof, which one can find in a paper by Hefliger in which is called, I think, differentiable cohomology. You get a chain map from this complex to the Durham complex of the matrix bundle. And you can prove that this map is a quasi-isomorphism of differential graded algebras. It's a sort of typical Van Nest type proof. And this will be repeated over and over again. Okay, now, in the paper with Alain on the Hopf algebras and local index formula, we constructed this map in a slightly different way from the Lie algebra cohomology to something else to prove that this is how we got the Hopf algebra, in fact, to prove that our index formula comes from that kind of cohomology. This is another version of that. And so the next thing is, let me see. Yes. The next thing, crucial thing, is Cohn's transfer map, I call it here, to cyclic cohomology. So in this game, I mean, this map phi is extremely important. And so I spent 2 slides by writing the rules because, so what Alain was doing was he was constructing this map by constructing first a sort of object over the algebra of forms, compactly supported forms on a manifold M, given any group of diffeomorphisms G. For me now it's the full group. And this tensor product is a differential graded algebra. So you just take, the exterior powers of the group ring generated by G, from which the unit is removed, and takes the tensor graded product with the algebra of forms, and then you form a bi-graded, bi-differential graded algebra by taking the cross product with the group itself. And here are the rules which give you the multiplication, if you want, and also the differentials. There are two differentials, D and one, which I call it delta here. So this is a total differential. So you get a bicomplex here. And each element in the cohomology, each cochain, if you want, in this bicomplex, defines a linear form on, this is on the dual of this, it's B, not C. C, sorry. On this bi-graded, bi-differential object, C. So this linear form, this should be a hat, not a tilde, is defined as being zero if phi is not the identity, and if it is the identity, is defined in terms of gamma, which is an element in the group cohomology coefficients in forms. Now I put gamma bar because you have to pass, I was talking here about this complex as what's called the non-homogeneous cochains, but you can also pass to homogeneous cochains by adding another copy of G. And this is what I call gamma bar. It's an equivalent definition. If you add to it the invariance of forms with respect to translation by one of the elements in the group. So this defines linear forms which have some property, linear forms on this bi-graded object, bi-differential bi-graded object. And Alain showed that they satisfy some basic compatibility rules with respect to the two differentials. And then using them, he defined the map phi. That's an explicit map. I mean, the cyclic cohomology of the cross product of functions on a manifold by a group of diffeomorphisms is by now computed in quite explicitly. But the computation, I mean, the isomorphism with something else is sort of not that explicit. So Alain defined an explicit map from this bicomplex bi-differential, bi-graded complex to the cyclic cohomology of the cross product by a very precise formula, which is I'm reproducing here. It's not a simple formula, but it's a very important one. So this gives a chain map, and it gives, in fact, it induces an isomorphism with a cohomology of the cross product localized as the identity element. And then this works not just for the cross product with the group, it works for any et al. Smooth groupoid with appropriate modifications. Et al. Smooth groupoid, Hausdorff or non-Hausdorff, with the appropriate modifications, it works in general. But I will stay grounded only in the cross product case with a group of diffeomorphisms. So we don't have to worry about technicalities. And now let me use this, Allen's map phi to show how one can get to in a natural way to the Hopf algebra. So again, I need some notation. The frame bundle for Rn is, of course, identified to Rn cross GLN. The matrix bundle is the quotient by ON. I'm working, I start with the most trivial connection, just the differential with values in GLN. And Gn is the group of diffeomorphisms. So the frame bundle has a canonical basis. These are the horizontal forms. These are the vertical forms. Their duals are the canonical forms, which are dual to the corresponding to the horizontals, and the connection forms are dual to this. I mean, the duality is between all these objects on this line and all these objects on the other line. Now, remember that we had a map D in the DuPont-de Rham complex, which was, let me get back to that and recall. I'm talking about this map D constructed with starting from a connection. The connection now is a trivial connection. The group G is the group of diffeomorphisms. And this is integration along simplices. You integrate the forms on the simplex part in T's, dt1, dtn. And this is how you get to the Bott complex from the Rham complex. Okay. And so if you take a cochain, which is in the image of that map D, and you compute what phi gamma is for that cochain gamma, what you see is you get an explicit formula of the following form. So first of all, so it's a linear, here, these are monomials, which are products of the following type of elements. A0, A1, AL, these are just, you can think of them as F0, then U phi 0, I mean, basic elements in the cross product. So a function times a representative of the diffeomorphism for each of the A's. Now, if you look at what these ages are, these are just obtained from operators which are like the horizontal and vertical operators applied to the function part. So f u phi star is like one of the A's. Star means that you just take the inverse of phi. It should, it's the same as u phi inverse. So you take these basic operators, y and x's. If you take brackets, then you will get some other operators which act on these basic elements in the cross product. These are multiplication operators with functions on the frame bundle. And the functions on the frame bundles are in terms of the jet, the first jet of the diffeomorphism phi. So what you get is not just these operators, but the algebra generated by this operator. So when I say the algebra, of course, you have to take all the brackets, because in particular, if you have an algebra, you can form the usual bracket. And when you form the brackets, then you'll get more functions of the form gamma ijk, except that you differentiate with respect to higher indices. So the brackets with the x's will give you higher derivatives here of the diffeomorphism, so higher jets. The brackets with the y's just move them around. It don't bring anything new. So now, how do these things appear? Oh, well, they appear because, remember, in Kahn's formula for capital phi, you have differentials, two kinds of differentials, one with respect to the group elements, but one just the de Rham differential. So when you apply the de Rham differential to function f, of course, you can express df in terms of the basis, canonical basis of the frame bundle. The canonical basis is, oh, I made a typo here. This little omega is theta. Xk, theta k, and then yij, omega ij. So this is how you get these operators. You get them from Allen's formula for phi because you have to take differential, de Rham differential. And then remember the rules for multiplication, you see them here. When you do that, then you'll get not only the vector fields, but also multiplications with the other operators. So what I am saying is that there is a whole algebra which appears if you just take the map phi and try to analyze it. And what is this tau? Tau is just the canonical trace which you have on the cross product. So this is what tau is. You restrict, in other words, you take the restriction to the units after you do the whole calculation here. I mean, you take this product in the cross product and then you restrict it to the units and integrate. And this is the canonical trace. Now, the algebra which I described on the other slide, generated by the those basic generators, it is a Hopf algebra, in fact, because you can copy a coproduct from the Leibniz rules, which they satisfy with respect to the action on the cross product algebra. Namely, if you take the action on a product, you get exactly how the coproduct should be defined and how you can also deduct the antipodes. There is an antipode. In addition, there is, besides the co-unit, there is another character which appears here, which is the extension of taking the trace of these generators, Yij. Namely, you get a character by taking the trace of Yij, and on the rest is 0. And with respect to this, you see that, so in other words, in Hopf algebraic terms, the cross product algebra is a module with respect, algebra module with respect to Agen. And it satisfies, and the trace on it satisfies an invariance condition with respect to this character delta, which I wrote here. Okay. So now out of this, not only you can get the Hopf algebra, but you can get what should be the cyclic object associated to this Hopf algebra to get the cohomology which you need, just by copying the rules from the embedding of the tensor product of Agen into the usual cyclic bicomplex of the algebra on which they act. So if you take this map, which we call the characteristic map, defined naturally by what we saw that it appears in the phi operator, the right-hand side, if you just take it and copy the rules, transfer them from this cyclic bicomplex to the left, you get a cyclic object, of course, cyclic object associated to the Hopf algebra Agen, which satisfies this basic, I mean, which is endowed with these basic operators, the deltas and the phases or cophase operators. You see what the cyclic operator should be. By the way, this S delta is not just the antipode, it's twisted to the left with the character. And so you get, if you take the associated bicomplex, BB complex associated to this cyclic object, its cohomology is by definition the Hopf cyclic cohomology of the Hopf algebra AGN with coefficients in this one-dimensional algebra module and or character if you want. And what we proved in the paper in '98 was that this is the isomorphic with a Lie algebra cohomology for the formal vector fields for AGN. And the periodic cohomology is like that. And in the relative case, of course, you get the corresponding isomorphism with the relative cohomology, the algebra cohomology. Okay, so that was in the paper 2. I put 3 here because I used some notation with a connection from the other paper, but the proof is the paper with Alain, the first one which I mentioned. All right. So moreover, if you look at the way in which this was obtained, then you can see that because it was by composing D with Cohn's map phi. So first D and then you apply phi. So if you look at them, you see that both of them are quasi-isomorphism. I mean, from the Lie algebra cohomology to the subcomplex, which is its image by the map of complexes script D, and continue to by inverting chi. Chi was a faithful map, so you can always invert it. So when you invert it, as I explained, you get in the cyclic complex of the Hopf algebra, because this is how it was defined, by inverting this. All right. So here is the outcome which I want to retain for now, that the Lie algebra cohomology, BRD, is isomorphic with this cohomology of the sort of restricted Bott complex to the image of D, but the embedding in the full differentiable complex is also a quasi-isomorphism, because we know that this is how, that was mimicking Dupont's proof to prove this with the Bott complex. Okay, so the whole thing is what I had in the third slide, or fourth slide. So this subscript D refers to the differentiable cohomology, differentiable in the sense of continuity with respect to the jet components, formal jet components. So if you compose this in this order, you get an isomorphism, induced isomorphism, which I'll call chi sub D, from the periodic cohomology of the Hopf algebra to the differentiable cohomology of the, to the cohomology of the differentiable Bott complex, say. Okay, for the matrix bundle on Rn. All right, now this was what we did, and it corresponds to, it's parallel to the Gelfand-Fuchs Lie algebra cohomology. Now I mentioned that there is a counterpart which is closer to the Weil algebra. This is what Sasha Gorokhovsky did shortly after, in fact, a year or two after we came up with the Hopf algebra cohomology for AGN. He found that there is a differential graded version of it, which looks more like the Weil algebra. Okay, so first of all, I should mention that one can develop the DG versions of the cyclic cohomology and of the Hopf cyclic, and by sort of natural definitions, but you will have triple complex, because since you are now having another differential D, instead of a double complex, you take triple complex. Now, when you work with complexes, you have to specify what kind of cochains. They will be finite, all finite cochains here, because otherwise you get cohomology which is different from what we need here. So what Sasha did was, first of all, because he's working with these finite cochains, he can relate the cohomology of the differential graded algebra, just like in the usual case, to the cohomology of the component A0. Namely, first of all, there is a natural embedding of A0, of the cyclic cohomology of A0 into the cyclic cohomology of the full thing. But more interesting, there is an inverse, which is quasi-isomorphism, which is constructed, for instance, by this formula. There are two ways of using it. I should put here little d, not capital D. Capital D, this formula makes sense for any derivation, but the derivation capital D, which I need here, is this little d, the differential. And what you get is a quasi-isomorphism, because it's inverse up to homotopy to the inclusion of the right-hand side into the left-hand side. Okay, so we have this natural contraction map R from the cyclic cohomology of the DG complex to the usual complex, A0. Now, if you look at the construction of a map, of the phi map, then what Sasha noticed is that this is in fact the construction of a cycle over the algebra, the cross product algebra between forms and the group G. So G is a group of diffeomorphisms. These are the forms, and you take the cross product algebra, then this object, which Allen constructed, is endowed with a cochain from this complex C constructed by Allen. This gives you exactly the analog of a cycle, the graded cycle over the algebra, basic algebra. But instead of being just an algebra, you start with a differential graded algebra because you work with forms. So this is why you get a bi-differential, bi-graded object when you construct a cycle over it. And if you have a cycle, then the cycle has a character. This is how Allen introduced the cyclic cohomology, in fact, by characters of cycles. And so with this interpretation of phi, what one can see is that Allen's construction and his theorem that you recover the cohomology localized at the identity, the cyclic cohomology, is the far-reaching extension of the theorem which he proved in the first paper on cyclic cohomology. He wrote that the Durham currents give you cycles over the differential forms on a manifold, and those cycles generate the full cyclic cohomology of the algebra of functions. Well, this is the analogous result, but not just for the functions on a manifold, but for the cross product by a group of diffeomorphisms acting on a manifold. And it gives you all the cohomology localized at the identity. So all the cohomology is generated by these kinds of cycles. Okay, so with this interpretation, one can retain, I mean, one can understand much better the meaning of the map phi. But as you can see, one can also define the differentiable version of cyclic cohomology. So now, if you have a Hopf algebra now, there is a differential graded Hopf algebra, then you have a corresponding Hopf cyclic cohomology for it, which is just adjusting in the natural way all these, the basic operators, little b, capital B by some degrees and stuff, and the differential. Now for us, the Hopf algebra will be the algebra of forms on GLN. Now it's important here to take all functions, all smooth functions on GLN, not just the regular functions. If you take the regular function, get an algebraic object, that algebraic object is still a Hopf algebra. If you take, you know, algebraic polynomials in GLN elements and determinant, the usual regular functions on GLN, you get a smaller algebra, Hopf algebra, but it's important to work with the full Hopf algebra. And so it's a Frechet Hopf algebra now, not just an algebraic, purely algebraic object. And for it, you can define cyclic cohomology, as I said. And you can also define the filtrations of this algebra, filtrations by degree, natural filtrations. And what Sasha proved about this object is that the cyclic cohomology of defined by these objects, the Hopf algebra with the filtration, recovers the Weil algebra cohomology in the relative case too, relative and truncated with respect to any truncation. Now, I'm not going to say much about the proof, but just two natural things. One is that the Hochschild complex of this, the Hochschild is a coalgebra, of course, is exactly the simplicial Duram complex of the nerve of GLN, simplicial nerve of GLN. So that's, not only that, but the cohomology, the Hochschild cohomology identifies with the cohomology of the nerve. But the whole theorem has a flavor of Van Ness because it's like the left-hand side corresponds like with the differentiable cohomology, and the right-hand side, it's a Lie algebra cohomology. Well, this is a differential graded version of Van Ness, if you want. Okay, now so that's the counterpart, the DG counterpart of the Hopf algebra AGN. Now AGN acts on the functions, acts on the cross product of functions by a group of diffeomorphisms. Similarly, this algebra acts in the following way. So if you form the corresponding group weight here, and if you take the first jet, this defines a map, because we are on flat space, this defines a map to GLN. And with this map, you can define the action of forms on GLN on cross product elements. So if instead of this omega, not an omega, var pi is called in LaTeX, alpha applied to such an element is you pull back the form, you multiply, you get a form on the group weight, and you multiply by omega. If you want to see it concretely, you take f times u phi here, you multiply this with the form alpha computed. So alpha is a form on GLN. Phi prime of x for each x is an element of GLN. You compute alpha, the form on that x, and you multiply with a function at x and with a u phi. So it's just a natural thing. There is again a natural closed graded trace on the cross product restricted to the unit, which is invariant with respect to this Hopf algebra. Epsilon of alpha is 0 if alpha is not a constant. So, because it's a co-unit in. Okay, so again, there is a tautological characterization, if you want, of DG Hopf cyclic cohomology. I don't know if Sasha got it this way, probably not. He just got the rules from our rules for Hopf algebra, but you can copy it by embedding in the same way in which we embedded the Hopf algebra, cyclic object for the Hopf algebra in the cyclic object for the cross products. And now, the next thing is that if you take, there is a counterpart to map to Allen's map phi, which Sasha called psi, and is defined. The definition is very natural. Psi of this guy is defined in terms of gamma bar. Remember, gamma bar is the form, is the cocycle viewed as a graded trace, partial graded trace on the character constructed by Allen. Okay, so with this natural definition, you get a chain map again from Allen's cyclic, from Allen's cycle to the cyclic cohomology. Now, the map phi is in fact the composition, not just in cohomology, it's on the nose, in fact. The retraction by R, remember the map R which retracts from the cross product of forms to the cross product of functions to the degree 0, is just this composition. And so, sorry, the DG counterpart of what I called chi-D, the isomorphism chi-D, can be defined similarly. So I skip all the definition of this E. I'm not giving it here. E corresponds to D, what I call script D before. There is a map which goes from the Weil algebra complex to this differentiable complex, and inside there is a subcomplex, and by a parallel construction one can obtain an isomorphism between this and the cohomology of both cohomology of Rn. So the difference between what we had before was that we have Rn here forms on Rn instead of forms on PRn, the matrix on Rn. Okay, so now one can define what the differentiable cyclic cohomology is. For me, that was a question which I couldn't figure out. How should one define what's the differentiable cohomology, cyclic cohomology? I mean, it's easy to define all the other differentiable things, but not for cyclic. Okay, so in this context, it's easy because you just take characters with gamma running through the cyclic subcomplex, through the differentiable subcomplex. By the way, this lambda means totally anti-symmetric, since you can always reduce to this smaller subcomplex, which was needed in Allen's construction. Okay, so now you have characters for both algebras, namely for M, yes, and I called the retracted X gammas are the psi characters, and Y gamma are the retracted characters, which are characters which land into the cyclic cohomology of the cross products with functions, not with forms. All right, so I'm getting now closer to the main point and the end of the talk. So I have these two isomorphisms, chi-D for the Hopf algebra, kappa D for the Sasha's algebra, differential graded algebra of forms. And because you have this isomorphism, you get an isomorphism between the two cyclic cohomologies, periodic cyclic, of the Hopf algebra and the other algebra, from these two, plus the fact that there is an isomorphism, well, canonical, natural, whatever, not just one. I mean, there are many ways to show that these two groups are isomorphic, cohomology group different. How? Well, for instance, by both of them are isomorphic with the cohomology of the double complex on the infinite forms. I mean, this is the trick which is explained in Heffliger's paper, which I already mentioned in some parallel context, and which mimics Van Est proof, in fact, for the theorem which I mentioned. So you have an isomorphism here, which gives an isomorphism here. So I call this the Thom isomorphism. Why? Well, because this is closely related to the Thom isomorphism which we needed in the with Alain in our paper, and we didn't get, in order to descend from the hypoelliptic, the index formula of the hypoelliptic operator on the frame bundle to the manifold on the matrix bundle, to the manifold itself. Now, let me show you why that construction should not be too easy, because look at the simplest example, H1, codimension 1, H1 and the Godbion-Weil. This is the Godbion-Weil, which almost everyone knows. Then if you apply the operator D, you get a cochain, group cochain with various informs. Now, if you take Alain's map phi applied to this guy, it's a co-cycle, in fact, you get exactly the image by the characteristic homomorphism from the Hopf algebra of one of the generators of the Hopf algebra. H, the cohomology of the Hopf algebra H1, the periodic one, is just two-dimensional, just like Gert-van Fuchs, is the transverse fundamental class, which I'm not writing here, and delta 1, which corresponds to the Godbion-Weil class by chi. But it's phi applied to the level of the frame bundle. Now, this gamma by tic-tac-toe in the double complex, as I said here, in this double complex, by tic-tac-toe, you bring it to this form of a two cochain of G1, but with various informs on the base now. That's a Bott-Thurston cocycle written here. Well, it can be, if you symmetrize it, and you will get exactly, and if you take phi at the level of S1, which is the base, not at the level of the frame, you get Cohn's version of Godbion-Weil in cyclic cohomology, in the cyclic cohomology of this algebra. Now, this phi is the same in this case with Sasha's psi, because you don't have room for more than degree 1 for forms. So it's already on functions. On the other forms, it's 0, 1 forms. Now, look at what's the difference between delta 1 here and what you have on the frame bundle. The difference is that here, the derivative of the logarithm is just phi double prime over phi prime. It's just the rational expression in the jet. In fact, phi prime is like the determinant in general, not just dimension 1. So you invert the determinant and you get derivatives, higher orders derivatives, first order, second order derivatives of the jet of phi. But if you look at the Bott-Thurston cocycle, or the equivalent to Cohn's Godbion-Weil class, you see the logarithm in it, which means that if you want to recover Godbion-Weil, you have to work with functions which are not algebraic, because you have the logarithm in the on GLN. It's so, and this gives in a way the Thom isomorphism, as I said, between the frame bundle, what happens on the frame bundle in terms of cyclic cohomology, differentiable cyclic, and what happens at the level of the base. So there is a transcendental element here, and that corresponds to the fact that in order to pass from the local index formula on the frame bundle, matrix bundle, if you want, down to the manifold, we had a formula over there. We needed a sort of cup product type of construction. And that cup product in the Kasparov KK theory the corresponding Chern character should be the descent of our formula upstairs. But that's a transcendental type of construction, because it will land in something like entire cyclic. So what I'm saying is that apparently it could be easier to do it just by understanding how to pass from a formula from the cyclic cohomology, differentiable cyclic cohomology, on the frame bundle, on the matrix bundle, to downstairs in a similar way in which you pass with this isomorphism here. So that should correspond to the Thom isomorphism in K theory or KK theory if you want, but make it simpler, because so that to me would suggest, so I mean, I have skip of the last slide just tells you how to construct all the classes, not just the God beyond they class. There is a construction of all the classes, which is in the last paper, which I mentioned at the beginning. But I just want to close to this idea, because that was the purpose of the talk, to sort of say that it's an interesting direction to look how to describe by sort of more algebraic construction the descent from the frame bundle here to this from the cyclic cohomology. Or in fact, you don't need that. You just need from this bicomplex to this complex something, a construction which should allow you to take any co-cycle on the cross product algebra on the matrix bundle, do some sort of cup product with something, the analog of the Thom isomorphism, but in cohomology, not in K theory or KK theory. Maybe it's more accessible. So I'll stop here. Thank you.
Thanks very much. Just want to ask around if there is any comment or question about your talk.
Okay. I'm listening. What is the boss saying?
No questions? If it's not the case, then we finish that for today, and we resume next week, and Walter will send around another email soon.
Okay, just one little thing which I should add, because I see this log. You see, if you take the algebraic Hopf algebra, DG Hopf algebra, then its cyclic cohomology gives you just the Chern classes. It's similar to what I did with Bahram in a paper with another Hopf algebra, which we called KN or something. Without the logarithm, we cannot get the secondary class. I mean, logarithm here will be the logarithm of the determinant of the in higher dimensions. But it's a transcendental type of thing. Okay.
Can I ask a quick question?
Sure.
So I don't know. Up to now, I only could glance at them, but there are recent works on the one hand of Toen and Toen Vetsozi, and on the other hand by Jonathan Block, who I guess is speaking tomorrow on another seminar on derived or singular foliations. I wonder if there is any known links.
No, this is not for singular. It's
yeah, but I wonder if
there is nothing singular.
No, but if it could be, I mean, you know.
Well, yes, maybe it could, but it should be developed in the regular, differentiable complex first. Possibly, yes, possibly, but even here is not. I mean, I'm not giving you a result. I'm giving you a sort of philosophy. I don't know.
Yeah, I understand. Okay, thanks. Yeah.
Okay.
Question on chat now. If this person can ask louder, or
This was Boris Tsigan.
Henri, can you?
Sorry. Well, the question was whether there are some known links or anything to recent works on derived or singular characteristic classes of foliations by Toen Vezzosi, and also Jonathan Block. That was the question.
No, I think it's too early to even contemplate this because
Okay,
Yeah.
okay.
it's not yet ripe for. I don't know what they do. First of all,
Let me just ask one small question, Riku. Somehow, you were saying that there is like this transcendental piece, and the other piece is more like the one we expect for the index theorem in the transversally elliptic.
yeah, sure.
So, I mean, might be one could use that to prove that you cannot get exotic classes.
I see. Maybe, yes, indeed. That would be a good idea because without this I mean, this is clear that, for instance, to describe the analog of delta 1 in the DG graded algebra, you'll have to put the log.
Yes, no, but that's what I have in mind. So if there was a good clean theory, of what you...
Yeah, you are right. That's probably the most feasible thing. I mean, you are right, absolutely right.
Yeah.
Indeed, I mean, if you work only with algebraic objects, then you only get Chen classes.
Exactly.
Right.
So that would be a very neat approach.
I agree. That should be a good principle.
Yeah.
Because, I mean, this log which appears here and in your formula too, I mean, shows clearly that.
Yeah, it's transcendental, yes.
Yeah, it's transcendental. Okay.
So Katya, there are some questions in the chat that you might want to answer. Or
I will address the question to Henri. The first one, can one use the RAM cohomology as a general procedure for finding the existence of Dirac monopoles?
Who knows?
They exist.
Because, I mean, it's not related to what I was talking about anyway. And
there is a second question which Golian might be able to answer, because the question is about the details of tomorrow talk.
That's in the regular, the ongoing online NCG seminar in North America. So if you want, the schedule is posted on Xiangtang's page in Washington University, St. Louis. I mean, if you just Google online non-commutative geometry seminar, so probably things will pop out. But if you cannot find it, you can send me an email. So
it's a good point. This is what Boris said, that tomorrow there will be a talk with some singular foliation stuff. Yes. So, right.
Okay, then I leave
back to back by coincidentally there will be back to back talks on characteristic classes of foliations. Okay. Nice to see you guys and girls.
Thank you.
Yeah, nice to see you.
Bye-bye.
thanks.
Bye-bye, thank you.
Bye-bye, thank you.
Bye-bye, thanks. Okay.